Okay, thank you. All right, so this talk's going to be about radio astronomy. So we're shifting focus. So first of all, what is it? Radio astronomy is the study of objects in outer space by measuring the power of their electromagnetic radiation at radio frequencies, and then making a variety of physical inferences about the source properties. Right? Our measurements are quantitative, and what the thing that we measure is called spectral power flux density. It's a unit of power, and we define what we call a Jansky as 10 to the power minus 26 watts per unit area and bandwidth. These are weak signals, right? The brightest radio sources range from at about 10 to the power 4 Janskys, and detection limits of the best instruments right now go to below a micro Jansky. So we already span at least 10 orders of magnitude in brightness. The way we make these measurements is by putting receivers at the focal points of large dishes to collect as much signal as possible. And we make measurements of this power at different temporal frequencies, as is shown by the different lengths of these dipoles in the speed. We also measure the E field in two orthogonal polarization, two orthogonal directions. And we do this to constrain the polarization angle of the incident E field. Right? So these are the two kinds of measurements we make. So with this kind of an instrument, the simplest way to make an image is just to do a raster scan in the sky, right? And if you have a small dish and a big dish, just like when you have a small lens and a big lens gives you more magnification and so more resolving power, and you see a lot more detail. But if you want more, you have to build much bigger dishes. And you end up in a situation where you cannot physically construct a large aperture or dish or a lens. And this is where we switch techniques and go into what we call aperture synthesis, which is where the connection to MRI comes in and medical imaging. It's no longer a direct imaging device, but what we measure are spatial frequencies, and which is exactly the same concept as sampling the K-space. And from that point on, reconstruction algorithms and all of the uncertainties involved, it's all the same. So we construct an aperture using a collection of smaller detectors. And I'll go into this in some detail at the end as to how this actually measures spatial frequencies. But for now, let's just take it that every pair of antennas measures one spatial frequency, and we measure as many of them as possible and then reconstruct. So how did all this get started? It was in the 30s when a radar engineer from Bell Labs was investigating the source of some strange static in one of their antennas. And they traced it to coming from the Milky Way based on the periodicity of the signal and connecting it to the sidereal rate of how fast the sky moves with respect to it. A few years later, Brock Reber was the first person who built a radio telescope and made the first all-sky map in radio frequencies. In the 40s, there was a group in Australia who were working with a radar antenna placed on a cliff overlooking the sea. And they were the first people to notice some strange bumps in their time series. Okay? They realized that it's coming from an astronomical source, and it was the result of an interference between the direct line of sight wave from the source to the antenna and the reflected wave off the surface of the ocean, which is coming to it with some delay. Now, delay is phase, right? And so they were the first ones to make the connection that what they're actually measuring is a spatial frequency. And they used this information to constrain the size, the angular size of the source on the sky for the first time. So it was then in the 60s that this technique was formalized by Martin Ryle and others, where you now intentionally made observations at spatial separations and combine the signals so as to convert the relative delay into phase information and intentionally sample spatial frequencies. And this is the work that established the field of aperture synthesis as we know it today in radio astronomy. So today, we still have single dish instruments, except that they become very big. The Green Bank telescope is the largest fully steerable parabolic dish. It's 100 meters in diameter. And anything beyond that has to be built into valleys and hillsides. Okay? So you cannot go bigger than this. So to synthesize apertures and to get more magnification than this, you have a whole lot of interferometers, which are these collection of arrays. There are several built out of dishes. At low radio frequencies, even building a single dish is difficult. So you then have what we call the dipole arrays, where each individual dish is itself synthesized by a whole bunch of just dipoles sitting on the ground. We then have what we call next generation instruments, which are all under the design and construction phase, which all promise to provide, or at least an order of magnitude, more sensitivity than the current instruments. Now, all of these instruments synthesize apertures, most of these instruments synthesize apertures of up to tens to several tens of kilometers in diameter. If you want to go beyond that, you can. There are continent scale instruments, as well as planet scale instruments, and even one where they put an antenna out in space to make long baselines between it and antennas on Earth. So what do we do with all of this? Right? Here's an example. So this is a picture of the M87 Radio Galaxy. It has a black hole at the center, and which is accreting material, and the infalling material interacts with the forces around it to produce jets, which send material out at relativistic speeds to form these bubbles and all kinds of things. So remember, our measurements are quantitative. So we measure the absolute power at different locations in the source. And you can do physics by calculating physical distances, considering light speed, and doing energy budgets. Do the theories that describe black holes describe the data for the amplitudes that you see far away from the black hole? Do all the theories combine, and does the data match? Are the theories right? What more should you put into the theories to make it match the data? All of these are questions people ask, right? And just for reference, the spatial scale in physical units of these structures are huge. This is 50,000 light years. So now you can study the time variability of these things. These two images show time variability at the very center, because that's where it's changing the fastest. The first image shows the base of the jet that's formed around the black hole. And the image at the bottom, of course, is the famous Event Horizon Telescope image of the radiation from outside the event horizon of the actual black hole there. And there's time variability in it. Now, I'd like to point out that the spatial scale for this black hole image is 0.006 light years. So look at the contrast in spatial scale. Moreover, these images were taken with very different instruments. The big green ones were taken with a very large array, which with an aperture of, in this case, between 1 and 10 kilometers. The first movie on the right was taken by the very long baseline array, which is a continent scale one, and the last one is a planet scale one. So to get a full picture of the astrophysics of the entire source, what is the source of the energy? What are the physics of the base? How does it feed these really large scale features? We make images that span many orders of magnitude, both in physical scale, as well as in angular resolution. So that's what you need to get the full picture. Now let's add more to this. Let's add polarization. Okay. Remember, polarization in our case is measuring the angle of the incident E field when it is polarized. And if you know the E field, you can infer the B field. And so these are maps where the lines show the magnetic field lines at different resolutions. And this is an image made by the Event Horizon Telescope collaboration. They have included some modeling as part of it as well, but these are really pretty pictures of the kind of physical information, quantitative physical information you can get about these sources. Okay, what else can one do? You can do spectroscopy or astrochemistry. When you have a molecular cloud that's sitting in the path of ionizing radiation from some burning star, it's going to excite the molecules, and you're going to get radiation at characteristic frequencies. So you can observe the spectra and identify the chemical composition of clouds. Now, these clouds are usually not stationary, they're moving, which means you're going to have Doppler effects. So these spectral lines are going to move in frequency. So if you've identified what they are by looking at patterns, you can now measure the Doppler shift and use it as a tracer of physical velocity. So the picture on the right is a velocity map of clouds in the Andromeda galaxy, and it very clearly shows you in which direction the galaxy is rotating. Red and the blue is towards and further away from that kind of thing. Here's another example of using velocities to trace three-dimensional structure. These are CO emission lines, and as a structure of velocity, as a function of velocity of frequency, you can actually trace. You can see that it's some kind of a three-dimensional spiral structure around a binary stellar system. You can make these kind of observations. There's more. You can study emission physics. And what do I mean by that? Different physical processes produce different characteristic patterns or shapes as a function of frequency, different spectra, expected spectra. So by making measurements at multiple frequencies, you can then observe and infer what are the physical processes that are happening in those locations. So these are two images, and in both of them, color in the image encodes spectral slope, right? So in the top one, it's an image of a galaxy cluster. So it's a cluster of galaxies with galaxies swarming around. And in this case, slope happens to encode the age of the source. And so you can clearly see when galaxies are moving, the heads and the tails are different colors. So you can see which direction, which ones are where is the energy being produced and where is the energy older and just decaying, and how fast it is happening given its length scale. You can do all kinds of things. The image at the bottom is of the galactic center. And in this case, again, slope indicates color. So it's almost a pseudo color image where red and blue literally translate to, is there more, is it brighter at the redder or the bluer end of the spectrum if you think of electromagnetic spectrum as red and blue. So you can visually tell that there are different physical processes happening in different parts of each of the sources, and you can, by knowing the exact slopes and color, you can map it to the physics. Finally, there are many ways to detect magnetic fields as well. So coronal magnetography is something where you can measure, you can probe the three-dimensional magnetic field structure on the surface of the sun. So these are solar coronal loops which have different magnetic field strengths at different heights above the surface of the sun. When you have different magnetic field strengths, the gyrosynchrotron emission is going to come at different frequencies. And so frequency is simply a tracer of three-dimensional structure of these magnetic loops. So you can make 3D maps of this. These also vary in time. And so there are some interesting things you can do while this varies. We also use the Faraday effect, where if you have linearly polarized light passing through an ionized medium in the presence of a B field, the E field, gets rotated. And there are ways to make observables as a combination of frequency and polarization to derive things like the line of sight integrated B field. So this map is an all-sky map of the B field of the galactic plane and everything around it, where red and blue are essentially towards us and away from us, and it's just encoding magnitude. It's an integrated, it's a metric that indicates line of sight B field. It's not a direct measure of B field itself. And finally, we can use the Zeeman effect, where if you have a transition in the presence of a magnetic field, your lines are going to split. The distance is proportional to the magnitude of that B field. And so by simply observing spectra and we can make observables as a function of, again, frequency and polarization, where we can directly read off and measure the in situ B field of the source. And so, for example, this picture on the right bottom is the map. The colors are a map of the B field in some star-forming region. And just to put some numbers, the red region is maps to about 80 microgauss. So you can make quantitative measurements like this. All right. So that's all about what we can do. And I'm going to spend the rest of the talk describing how we make the images and the image reconstruction side of it. Okay. So this is going to be about this method of aperture synthesis, where we use a collection of dishes to simulate or synthesize what we would like to have, which is a much larger dish. All right. So when we have a collection of antennas or receivers or detectors, you can think of every pair of detectors as being sensitive to a different spatial frequency. So the game then, of course, is to find as many such pairs as possible at different distances and orientations to be sensitive to as many different spatial frequencies as possible. This is similar to what many might know as the Young's double slit experiment, where if you have a plane wave incident on a pair of slits, you get an interference pattern whose wavelength is inversely proportional to the distance between the slits. So conceptually, it's like that. Practically, how do we do this? We take the voltages incident measured at each pair of antennas, and we basically just multiply them and integrate over time. Okay? Operationally, that's all we do. How does this measure a fringe? Think of an incident wave coming in from some direction on the side. Right? The plane wave hits one antenna first and then the other. So there's a delay involved. And delay translates to phase. Okay? So if you have radiation from different points in the sky, they all come in at different phases, which correspond to different locations on this fringe band. So we first have to steer the instrument. So let's pick one direction, say this big yellow star here, as the center of our image. That's where we're going to point. So we actually, what we do is, since it's going to hit one antenna first and then the other, we intentionally delay the signal of one side so that for radiation coming from the direction that we want to make an image at, we have taken out the phase delays, we've taken out the delay, and which means what we measure here is the amplitude at the peak of one of these fringe patterns. It's the maximum amplitude. From then on, signals from sources away from that center are going to reach your antenna pair with some relative delay. And that information, the sum of all of that, gets encoded in the phase of this quantity over here. And that basically gives us now our amplitude and phase of the fringe pattern measured by each pair of antennas. Okay. So now geometry tells us what the fringe pattern actually is, geometry of the spacing between the two dishes. And this number gives us the amplitude and phase. Okay, so now we have all of the ingredients needed to put this on K-space. So here is a little schematic to show that for this exact example, where do things fall on the K-space? If you look at the top two antennas and the top fringe pattern, let's say this almost horizontal vector, it goes and points to a location in the far right of this K-space. And the complex number that you measure is what we place over there. The example on the bottom right, which is at a different angle, maybe goes to this bottom left quadrant here, and the third one up there. The little gray spots here are just the complex conjugates, because by measuring one point, you implicitly measure the complex conjugate as well, simply because power is real valued and image is real valued, so the transform has to be Hermitian. So this is how we build up our K-space. So I'm going to show you a couple of slightly more realistic examples of what the K-space looks like. And that's going to show up in the middle here, and what the images look like that we generate. The image on the top left is just 4 spots, which is our reference truth image for this simulation. So if you had just 2 antennas, you have one baseline. The baseline is a pair of antennas, and it's basically one fringe pattern that you're measuring. And if you add 2, 5, 11, you get more, and 27, you get more. And that's how you fill up some amount of K-space. Now, I stopped at 27 simply because the Very Large Array instrument in New Mexico has 27 antennas, but it depends on the number that you have. But what you can see here is this sampling is pretty sparse, but it is the best that one can do at a single frequency and at a single instant in time. Okay? But fortunately for us, the Earth is a rotating platform with respect to the sky, and therefore, as a function of time, the relative projected distances between antenna pairs as seen from the source keeps changing. And so you essentially fill up different parts of K-space simply by waiting over time. And so 2 hours and a 4-hour observation ends up filling up this K-space reasonably well. There are still gaps all around the edges, and more importantly, there's a hole in the middle. Okay? There is a finite, you cannot put dishes closer together than touching each other. So you can never measure the zero spacing, which means you never have a measurement of the absolute total brightness. And remember, our images are supposed to be quantitative, so we need to know that number. So this is an actual problem we have to deal with in image reconstruction. But anyway, let's assume this is the best you can do with the raw data. Anything beyond this goes into image reconstruction and modeling. Okay, and I'll go there next. But before that, if you look at the shapes here, you can see the structure, these 4 points, but you can see the same characteristic pattern repeated around all of them. Okay? Visually and physically, this looks like a convolution, where you've convolved the true sky image with a point spread function. And the point spread function is this pattern, which is the Fourier transform of your sampling pattern. So in a 2D approximation, you can think of the observed image as a convolution, as a result of a convolution. And so the first algorithms that came up for the reconstruction used this physical interpretation and implemented what are called deconvolution algorithms. They're iterative. So that's how the algorithms got started in this field, but they have now moved to being more formally defined, because a 2-dimensional approximation is not all there is to it. But that's where it started, and those approximations are a fantastic first start on the algorithms. So the true measurement equation, or the forward problem in optimization language, is this, right? I'll walk through all the pieces. So you have the sky brightness, so that's the signal we want. You have the K-space sampling function. You have a 3-dimensional integral. And this three-dimensional integral is a combination of the two-dimensional Fourier transform plus an extra phase term that tells you about the difference between an actual three-dimensional curved sky and a two-dimensional tangent plane image of that sky. So the 2D to 3D relationship is encoded there. You then have these M's, which are basically instrumental and atmospheric effects that need to be also corrected for. And the picture at the bottom left shows just schematically that most of these things can be modeled as instrument response functions. So now if you take away the physics, this functional form is exactly the same or very similar to that of MRI, and which is where the structures of solutions and algorithms, there's a good similarity, and that's a point of interest for several of us. So how do we solve this? We first take out one of the M's, the one outside the integral, through an independent calibration process. We then take care of all the transforms, so gridding the data onto a regular grid using gridding convolution functions that are derived from these M's here so that you can undo certain effects. Once you make an image, you then do the reconstruction of the model. So we have these three separate stages, and we typically iterate through them in various sequences, and eventually things converge. Okay, that's basically it. More formally, we can describe this as solving a system of equations where A is a measurement operator. The inverse of A strictly does not exist because of the unmeasured information, and so your solution process is an iterative optimization algorithm. We have all the usual ingredients, which is there's a data regularizer, which is chi-squared. We have various kinds of sky models, different optimization algorithms you can apply to it, and a host of instrumental corrections that have to be also applied at the same time. And the picture on the left just shows that we also treat this as subproblems, where we have the data to the image transforms and the L2 as one subproblem. And then once you go to the image domain, you have another subproblem, which is the sky model and the part where the priors and the regularization and the biases and all of that come in. And we separate these two. One reason why we separate these is that our data volumes are large. And so we want to minimize the number of times we go through the data. So we actually do this outer loop only a few times and this inner loop many more times and more times. Okay. So what comes with such variety in algorithms? Different answers. Okay. So different algorithms are going to give you different images. And there is no clear way to tell which one is right. And so we constantly have to deal with algorithmic uncertainty. So of course, you can do synthetic simulations and validate your algorithms that way. But when you're looking at something on sky, you really don't know what you're missing. And remember, our measurements are supposed to be quantitative because you need absolute numbers to do the astrophysics with them. So we spend a great deal of time trying to characterize the angular resolution, the spatial scales that are present in the data. People try to understand what the different regularizers and bias terms are actually doing and how they affect this so they can make educated judgments about how to correct or adjust the amplitudes that they see to get to something that they use quantitatively. This is an ongoing situation. Let's put it that way. Here are a couple of 4 pairs of images which just show you the different kinds of instrumental corrections that we have to apply. So they are left and right pairs before and after. So the first one is wideband frequency dependent effects. The left one is we don't measure the zero spacing in the spatial frequency plane, and so there are ways to get information from single dish instruments to fill that in and do a joint reconstruction. And there are various wide field instrumentals that you can correct. All right, so where's the field going? One direction is the bigger is better. So there are proposed larger instruments with up to 2,000 dishes and 200 dishes, so really large instruments compared to the 20s and 30s that we have right now. So an order of magnitude more sensitive. So why do they need to be more sensitive? Well, they need to be more sensitive so you can detect fainter sources, and that can be done with lower image noise. Lower image noise, since it's Gaussian random noise in an actual measurement, can come by taking more and more data to just beat down the noise to square root of n, right? That's the mean. Lower image noise also means that more and more subtle instrumental effects and other problems are going to show up above the noise level, and so you're going to need more complicated algorithms to fix that. So it's almost a double whammy. To get better, detect fainter sources, you have much larger data volumes and greater algorithm complexity. And so there's a lot of R&D going in how to make that work together. So R&D continues on the algorithm front. And our field is only beginning to explore the use of machine learning. There are some very promising results, mostly from the groups which are working with a smaller number of antennas, like the Event Horizon Telescope group, where they can experiment easily and do the more interesting algorithms. But in our field, I mean, for the much larger instruments, it hasn't become mainstream yet. And this is one thing that some of us are rather interested in learning from the experience built up in this group. So yes. Our data volumes are large. Current instruments, data sizes are up to hundreds of gigabytes, whereas the newer instruments can be much, much larger. And our image sizes are much larger as well. So we are restricted almost. So we have to develop computing and algorithms at the same time. And in fact, for practical use, our algorithms, which algorithms actually are usable, depend on how easily scalable their implementations can be. And so we have a nice interplay between this. And finally, is automation. We have so many stages and so many parameters to tune that we have data reduction workshops where we teach people how to decide what to do. And so there is some effort going on to how to automate this. And there are production pipelines in operations which hard code specific sequences through a decision tree almost. And there is R&D going on how to automate it. So this is where the field is. From a perspective of algorithms and computing and image reconstruction, there's a lot to do, and it's an exciting time. All right, I'd like to end by, this is the acknowledgements. And first of all, I'd like to thank Dan. We had the pleasure of meeting him a couple of years ago as part of the Cells to Galaxies. And since then, he's been absolutely wonderful in helping us explore the relation between medical imaging and radio astronomy, and essentially talking the same language. It's been great, and I hope we can continue that. I'd like to thank him and the organizers of the I2F workshop for including us in this group, and other colleagues as well. That's all I have. I'll leave it with this slide, and thank you for your attention.
So thank you very much for this terrific talk. Questions?
Fascinating talk, thank you. I was wondering if an array is like an eye, is there any sense of binocularity? Can we do two arrays looking at the same object and get some additional information? We also didn't talk at all about the Z dimension. I guess everything is XY, but I'm guessing there is an interesting Z.
Okay. Most of it is XY because it's so far away that you can't sense Z directly. But some of it is done for, so parallax. So what people do is the distances are so large that to actually use the Z, you need to be really far apart. And people do that by using the Earth's orbit around the sun. So there are observations where you take an observation now and take another observation 6 months later. And you can use parallax measurements to constrain locations at a much better angular resolution than the resolution of an individual observation itself. That's basically, I think, the most prominent use of the third B.
And about the first question of using two arrays looking at the same object, does that happen at all? Because it looked like all the reconstructions were really from one array.
It's usually from one array. We do combine data from multiple instruments, multiple telescopes, and data taken from multiple times. So there are all kinds of joint reconstructions we can do. There are things like mosaics, where we make mosaics of images. And so you can think of those as combining essentially completely separate data sets. Could be from the same instrument, could be different. To fill in the zero spacing hole in our phase space, we combine single dish instruments because they are sensitive to the zero scale and low spatial frequencies. And interferometers do not measure the zero, but they measure the higher ones. So you can get constraints from both these together to do that. So in that sense, we do. It's not really more of a 3D thing. It's more to fill in the spatial frequency thing.
So fantastic talk, and the way you simplified it was really amazing. One question I had is, you mentioned these arrays of dishes and detectors that are there and connecting together. It's an option that what if these detectors were placed on say on the moon or another planet or somewhere, and you kind of alluded to one being in the space, but what if it is far off? Would the data be more stronger, and can that be collected together?
In principle, yes. And so there is talk. So there is talk of putting an interferometer on the backside of the moon, because that is for different reasons, but because that is more shielded from radio frequency interference than anything else around the planet or on the planet. But the space VLBI, for example, is a thing where you have antennas out. In principle, yes. What you will get from that is angular resolution. So for the science cases that need more and more detail, that's what you'd like to do. So like the black hole, that was the first, that angular resolution was achieved by literally using a planet scale instrument. So if there are science cases that require even more, that's what those are for. But then practical realities come into play. Even putting that first one antenna out in space and VLBI is a very recent technical achievement. And so that's where the field is. Yes. In principle, yes. But
Brief question.
Quick question. If you had all of your dishes on the line, what's the proper alignment east-west so that it would look like this?
I think an east-west array, so the way you translate physical location of the antennas on the Earth to filling up of the K-space is a geometrical transform and projection with two rotating coordinate systems projected onto each other. So with a line, if you have an east-west array, and if you put it on away from the equator, you get circular patterns in the K-space. So there are optimal places to put it. I mean, ideally you put it at the North Pole so that it's rotating and you can get it at all directions, but practicalities come into play. What we typically do, I mean, what the examples I showed you were a Y shape, which when they were designed seemed like a good compromise of orientation agnostic as well as filling up spatial frequency. Most of the newer arrays are just a completely random sampling within some aperture space. And the randomization there is just choosing random and following topography and all of that is generally good enough to get as good a spatial frequency sampling as is possible with a finite number of detectors.
Brief, naive question, great talk, thank you. The videos from the Event Horizon Telescope, like the one that you showed, they have this effect where the light seems to be emerging over an arc of like 180 degrees, but then it will rotate or flip. Is that the real effect, or is that light whipping around the orbit of the black hole, or is that because we ourselves are rotating on Earth? What's creating this effect where the light is only emerging, it seems, from sort of one arc and then the other and kind of rotating around the black holes?
So from my limited understanding of that, I think it is an actual reflection of different matter accreting into the black hole and interacting with the forces around it. And so they are measuring an actual physical, it's brighter at this point in the ring, and then it's brighter in another portion of the ring. So it's an actual, I think it's an actual physical thing and not just an optical effect.
One last question.
In the reconstruction world, you can either go to Fourier base or sometimes you do model iterative reconstructions. Do you ever use the iterative model reconstructions? And is there any reason to use one versus the other?
Okay. Yes. So we do sometimes skip the imaging stage altogether and directly model the physics from the data themselves. This is not really mainstream. I think it was done for the smaller data sets where you can actually do an iterative optimization by directly fitting physics and sky parameters by iterating through the data for every step of your convergence. But I think that's where one is. So yes, in principle, that's possible. But most of the mainstream instruments still go through the stage of making the image first and then inferring the astrophysics from it. Did that connect to what you were asking?
So there's no more questions. Super fast, please.
It's very fast and very so thank you very much for the talk. In between the telescope and the target, there are many things going on and many stars also behind the target as well. How do you dodge all of that and focus on the aim?
We cannot dodge any of it. And so, yes, so there is refraction. So one of the examples is the ionosphere refracts all our signals. And so at certain frequencies, that's a problem. At certain other frequencies, it's not a problem. The transmission is good. But where it is a problem, we now have to model and correct for that as well. So we use external models of the total electron content of the ionosphere, which from other sources, from other geophysics, and there are people who study the atmosphere who make these models. So we take that information and put that into our instrumental correction terms as best as one can. This other thing we can do is to solve for some of these terms from our data itself. So remember I said our data, we separate our problem into different subproblems, right? And we iterate through them. You can do various things of keeping various terms fixed and solving for the third one. So we do all these kinds of games to sometimes try to solve for distortion effects from our data themselves and then correct them and keep going. So we try these kind of things, but otherwise we cannot avoid it. And another thing we cannot avoid is radio frequency interference from, cell phones, TV, whatever, all of these things. And now the LEO satellites networks, which all are radiating in exactly the bands we want to observe. So there's some interesting studies going on as to how to dodge that.
Thank you very much.
Okay, thank you very much again for this fantastic talk.